All right, so moving on, we're going to talk about molar mass, which I have said several times by accident when talking about molecular mass, but now we're actually going to introduce the topic of molar mass. So molecular formulas, again, tell us the amount of each element present in one molecule of the compound. We can also use the molecular formula to calculate the molar mass of a compound, which is the mass in grams of 1 mole. So this is the mass in grams of 1 mole, whereas the molecular mass was the mass in AMUs of one molecule. Okay, so the reason that I use these terms a little interchangeably is because the molar mass is equal to the atomic mass, but with different units. So the mole of carbon, so by definition, we learned this back in chapter 1 or 2, by definition, the mole of 1 mole of carbon-12 weighs exactly 12 grams. And that's why the molar mass of carbon is equal to its atomic mass. So the molar mass in grams is equal to the atomic mass in AMUs, is how I should have that written. So the molar mass of carbon is 12 grams. The atomic mass of carbon is 12 AMUs. So it's just, the difference is whether we're talking about 1 atom or 1 mole of atoms. So likewise, 1 calcium atom weighs 40.08 AMUs. 1 mole of calcium atoms weighs 40.08 grams. 1 sodium atom weighs 22.99 AMUs, and 1 mole of sodium atoms weighs 22.99 grams. So that's why I tend to use them interchangeably, because they pretty much are interchangeable, okay? You just have to understand the concept first, which I apologize for using them interchangeably before we were ready to do so. In general, an element's molar mass in grams is equal to its atomic mass in AMUs. And a compound's molar mass in grams is equal to its molecular or formula mass in AMUs. So let's look at water, for example. So for example, 1 molecule of water is made up of 2 hydrogen atoms and 1 oxygen atom, as you know. Therefore, the mass of 1 mole of water, the molar mass of water, is equal to the mass of 2 moles of hydrogen atoms plus the mass of 1 mole of oxygen atoms. So we take our molar masses of the elements, 2 moles of hydrogen in 1 mole of water, and multiply it by the molar mass of hydrogen, and 1 mole of oxygen in 1 mole of water, multiply it by the molar mass of oxygen. Our moles cancel out, and we end up with 18.02 grams as our molar mass of water. And although the term molar mass specifies that the mass is for 1 mole of a substance, which means we might not need to say that it's, we only need to say that it's in grams, because we're already specifying that it's for 1 mole of the substance, we usually use the units of grams per mole, because most of the time when we're using molar masses, we're using them to do calculations involving moles, a certain number of moles of the compound. So to use, or to go between moles and mass, we use units of grams per mole instead. Well, we really only need to say grams when we're considering a molar mass. Okay, so I'm always going to say grams per mole from here on out. Alrighty, so the molar mass of a compound can be used to convert between moles, atoms, and mass in grams of a sample. So really it's between moles and grams, but since we know that Avogadro's number ties together moles and atoms, we can now go between all 3. But to start, let's look at moles and grams. What is the mass of 0.0841 moles of sodium chloride? So our first step is going to be to find the molar mass of sodium chloride. And we can do that by looking at the periodic table and adding up the molar masses of our elements. So sodium chloride has this formula, as you know, is NaCl. So we've got 1 mole of sodium and 1 mole of chlorine, and we multiply those by our molar masses of sodium and chlorine. So the molar mass of sodium, 22.990 grams per mole, and the molar mass of chlorine is 35.45 or 35.453 in this case if we get an extra sig fig in there. So our moles cancel out, and we would technically end up with grams, but we're talking about 1 mole of sodium chloride, so it's okay to keep moles in there. But we don't have moles of sodium or chloride anymore. We have moles of sodium chloride, the compound. Okay, so we add all that up and we find that the molar mass of sodium chloride is 58.443 grams per mole. So now our question gave us 0.08141, 0.0841 moles of sodium chloride. So that's our starting number. And we want to find mass in grams, so we have to write our molar mass this way so that we can cancel out moles and end up with grams. So we multiply by our molar mass, moles cancel out, and we end up with 4.92 grams of sodium chloride. Our question started with 0.841 moles, so we have 3 sig figs in our answer. Okay, awesome. So your book goes on then to show you that you can convert between mass, moles, and then going all the way to particles, which could be atoms or molecules. Basically, formula units in general is the more general term. So you can do that, and you can practice this problem on your own if you'd like. How many atoms of calcium carbonate are in 0.967 grams of calcium carbonate? So I'll give you some hints. Calcium carbonate, calcium is our 2+ ion because it's in group 2. Carbonate is one of our polyatomic ions you need to remember. It's CO3, 2-. So we got +2 and -2, so we can combine them into calcium carbonate without any subscripts. So that's our formula for calcium carbonate. So what are our steps in this process? We start with a mass. That's what we have in our question. And then to go to moles, we want to divide by the molar mass. So we got to find the molar mass of calcium carbonate. So I'm going to let you guys figure that out. First, you want the molar mass of calcium and the molar mass of carbon and the molar mass of oxygen. And then there's 3 oxygens from our subscript in carbonate ion. So you need 3 times that molar mass of oxygen. And then you add all that together to get the molar mass of calcium carbonate. Then you have mass divided by molar mass gets you to moles. And you want to go to atoms. Sorry, it shouldn't even be atoms. It should be molecules. How many molecules of calcium carbonate are in that amount? Because calcium carbonate is a molecule. It's not an atom. It is a compound. So how many molecules? So then you're going to multiply by Avogadro's number because we're going in this direction across this flow chart. So I'll let you guys try that right now before I give you the answer. Okay, so hopefully you've worked on that now. So the molar mass of calcium carbonate, if you calculate it out, should be 100.09 grams per mole. So we want to start with our mass, so 0.967 grams divided by this molar mass is going to give us moles. That's going to come up to the numerator. And then moles, we're going to multiply by Avogadro's number, 6.022 times 10 to the 23rd. And that's going to be molecules in this case per mole. And then moles are going to cancel out. So 0.967 divided by 100.9 times 6.022 times 10 to the 23rd molecules. And your answer should be 5.82 times 10 to the 21st molecules of calcium carbonate. All right, so check to see if you guys got that answer. We'll keep going. Alrighty, so I had mentioned this a little bit before, how empirical formulas, we can use empirical formulas to get percent composition and molecular formulas to get percent composition. But when we're going backwards, when we want to find molecular formulas, we should start with empirical formulas, okay? So the first thing we want to do is to find the empirical formula from percent composition. So a common goal in chemistry laboratories is to determine the empirical formula from percent composition of its elements. So this is kind of what I was getting at when I said we were going to start doing combustion analysis, but that's a bit later. We're going to start easier than that. So in a sense, this is a reverse of the process that we used to determine percent composition. Now we're going backwards. If we're given percent composition of an element, we assume there's 100 grams exactly of the sample, which gives us the mass in grams of each element. If there's 100 grams exactly, then instead of 100%, we have 100 grams. And instead of whatever percent of elements, we have whatever grams of that element. All right, then we use the molar mass of the elements to end up with moles of the element. And we calculate a mole ratio based on those number of moles. So we find the amount in moles of each element and we compare them to each other to find the mole ratio of each element in that compound. And that gives us our empirical formula. So let's see what that looks like, okay? We're going to get to that in a little bit, but let's continue the process. So after we find our empirical formula, we want to get a molecular formula, most likely. So what do we do then? Let's review. Empirical formulas give us the simplest whole number ratio of the atoms of each element in a compound. And empirical formulas and molecular formulas are not necessarily the same. So this is a molecular formula for cyclopropane. This is a molecular formula for cyclobutane. These are two hydrocarbons. You don't need to remember them, but these are two molecular formulas, but they both have the same empirical formula because both of these can be reduced down to CH2. There's twice as many hydrogen atoms as there are carbon atoms in the empirical formula for these compounds. The molecular formula, as we know, is the whole number multiple, the molecular formula is the one that describes the compound in more detail. And that's what we usually want to find in the end, because that gives us the most information about the molecule. So how are empirical formulas and molecular formulas related? Numerically, the molecular formula of a compound is a whole number multiple of its empirical formula. So, like I said, this cyclopropane has an empirical formula of CH2, and if we multiply, it's kind of weird. We're not really multiplying because these are atoms, but if we multiply the empirical formula by 3, that means we multiply each subscript in the empirical formula. There's a 1 here that we don't really write. So we multiply those subscripts by 3 and we end up with C3H6, which is the molecular formula of cyclopropane. So cyclopropane's molecular formula is a whole number multiple of its empirical formula. And that's how we're going to go from empirical formulas to molecular formulas. All right, so this comes from your book. If we know the approximate molar mass of a compound, we can determine the molecular formula from the empirical formula. Here's a different example. Instead of cyclopropane, now let's look at glucose. We mentioned glucose at one point in a few lectures ago, maybe. The molar mass of glucose is about 180 grams. The empirical formula, if we divide all of these by their common denominator, which is 6, we get CH2O as the empirical formula for glucose, and the empirical formula mass of that is 30 grams. We have 12.01 grams from the one carbon atom, 2 times 1.008 grams from the 2 hydrogen atoms, and 16 grams from the oxygen atom. So that adds up to 30 grams, the empirical formula mass of the empirical formula for glucose. So to determine the molecular formula, we first divide the molar mass by the empirical formula mass. So we take our 180 grams, divide it by 30 grams, and find out what that whole number ratio is between the empirical formula and the molecular formula. This tells us there are 6 empirical formula units per molecule in glucose. So there we can have 6 multiples of this empirical formula in one formula unit of the molecular formula for glucose. So we multiply each subscript by 6, and that gives us the molecular formula of glucose if we were pretending that we didn't know what it was. Okay, cool. So now let's solve a problem. All right, so you guys can pause and try and work this problem out yourself, but I will show you what to do because this is pretty new for us. So the analysis of a compound, which is composed of xenon, oxygen, and fluorine, shows that it is 58.80% xenon, 7.166% oxygen, and fluorine is the remainder. So this compound is 100% composed of its elements. So fluorine, being the remainder, has to be 100% minus 58.80 minus 7.166. So we're going to subtract those other percentages to find the percentage of fluorine. So let me do that real quick on my calculator. And I found that means that we have 34.034% fluorine. Okay, so now we have all of our percentages for our elements. And we also know that the molar mass is 223.3 grams per mole. So let's see what the molecular formula of the compound is. So first we want to find the empirical formula, and then we're going to compare it to this molar mass. All right, so to find the empirical formula, we want to assume that we have 100 grams of our sample. So that means that we have 58.80 grams of xenon. We have 7.166 grams of oxygen and 34.034 grams of fluorine. So now we want to find those mole ratios that I mentioned. So we need to find the number of moles of each of these elements. So we divide by our molar masses of these elements. So xenon, we're going to divide by 131.29, grams, and moles goes on top. Oxygen, we're going to divide by 16. I'm just going to round it to 16.00 because that's what we've been using. So 16.00 grams. with moles on top. And fluorine, I'm going to do 18.998 grams with moles on top. Okay, so we divide all those numbers and let's see what we get. All right, so this first one, I got 0.4479. Sorry, my pen's not working. Moles. So 4479 moles of xenon. What's our next one? So 7.166 divided by 16. I got 0.4479. Wow, okay. Moles of oxygen. And lastly, 34.034 divided by 18.998. This time I got 1.791 moles of fluorine. All right, so to find these mole ratios, we're going to divide all of these by the smallest value. So the smallest value is going to be this 0.4479, which is the same for xenon as it is for oxygen, if I can write with my pen. Okay, so that's going to give us 1 mole ratio of xenon. Same thing here, 1 mole ratio of oxygen. And how many mole ratios of fluorine do we get? So 1.791 divided by 0.4479. All right, cool. So that comes out to 4 moles of fluorine. So for every 1 mole of xenon and 1 mole of oxygen, we have 4 moles of fluorine. So that gives us an empirical formula of xenon, oxygen with 4 fluorines. So xenon OF4 is our empirical formula. And now let's see what the empirical formula mass is. So we want to find the mass of 1 unit of this. So let's see. So we've got the molar mass of xenon plus the molar mass of oxygen plus 4 times the molar mass of fluorine because of our subscript from our formula. So that's 131.29 plus 15.999 plus 18.998 times 4. So I'm going to put that. So I'm going to put 18.998 times 4 in parentheses and then add them all up. And I got 223.3-ish grams per mole. So our empirical formula and our molecular formula are the same. So this is our empirical formula and our molecular formula. So we don't need to multiply our subscripts by anything further to get the molecular formula. We are done. So in this case, same molecular formula and empirical formula. And our final answer is this, xenon OF4. All right, and then this is just a summary for you guys of the steps that you need to calculate the molecular formula from the percent composition. So you're given a percent composition. These first 3 steps get you to the empirical formula, and the last 3 will get you to the molecular formula. So you'll want to be practicing this for your homework, and we'll practice it tomorrow in class on some reef questions. All right, see you then.